Hopefully by now, you are familiar with the capabilities of both Creo Parametric and MathCAD. Let's see how we can leverage the combination of the two tools to help us with everyday engineering tasks. We will use an example from the electronics and high-tech industry. Let's say I'm a mechanical engineer at a cell phone company. As new phone designs come out with new hardware, my team is responsible for designing a case or a shell to house the phone. Many requirements will govern how the shell looks. For one, we need to make sure that it can contain the hardware geometries. Thermal requirements will restrict what materials we can use. It might also affect the geometries as well. The industrial engineering team will throw in some ergonomic and aesthetic considerations. For this demo, we will consider a simplified case where the basic shell has already been designed. It has already been approved by the electrical team as it properly houses the electrical hardware. Analysis has already been done on the material properties to show that it can handle and also remove the heat generated from the hardware. Ergonomic friendliness has been checked. There is one last final requirement to meet, and that is if it can withstand certain stresses applied to the sides. As the mechanical engineer, I want to make sure that the case will not buckle under the maximum specified stress. The thicker the shell is, the more stress it can withstand. I can analyze this by using the elastic stability equations. I can find these equations in the O'Rourke's Formulas for Stress and Strain handbook. I will approximate the shell as a rectangular sheet and let it undergo uniform loads on both sides. This will give me a worst-case scenario calculation. Let's start in Creo. Here we have a part representing the basic shell that has already been designed. It already has all the necessary geometries to house the electronics. What remains is determining the thickness of the shell. At the moment, the shell is 0.02 inches thick and is specified by the thicken feature. Take a quick mental picture of how the shell looks right now. We will be changing it very shortly. We want to calculate the critical stress that will cause elastic instability in the shell. To do so, we will use MathCAD. We can install a MathCAD analysis feature right into the Creo part. Let's go ahead and edit the definition of this MathCAD analysis feature and see what it returns. By editing the definition, Creo automatically brings up MathCAD with the worksheet that I previously specified. Let's scroll through this worksheet. This worksheet contains the template for formatting the header and footer of my document. I have inserted some images into the body of the worksheet to help us visualize the problem we're trying to solve. I can put in the known parameters, including the geometry of the shell, which we have approximated as a rectangular plate. Note that we give an initial guess of 0.02 inches, just like the current value specified in the Creo part. Since we have already picked a material, we can input the Young's modulus and the Poisson ratio. Next, we apply the equations found in O'Rourke's handbook for this particular problem. We see that this plate with 0.02 inch thickness will start being elastically unstable at 0.384 megapascals. This may be sufficient for one design, but say I've been told that we want to make the phone extra rugged. Maybe this is a phone that will be targeted at extreme sports fanatics. We can take advantage of MathCAD solver to calculate just how thick the shell needs to be for a given maximum stress value. At the moment, the solver is solving for a maximum stress of 0.5 megapascals. This results in a shell thickness of 0.023 inches. Let's take the maximum stress up to 3.5 megapascals. You will see that the thickness jumps up to 0.101 inches or 2.56 millimeters. We go ahead and save this MathCAD worksheet and go back into Creo. We hit the Compute button to pull the MathCAD values into Creo. Note that we get the same 2.56 millimeter thickness. We accept these changes and let Creo regenerate the model. Hopefully you can see that the shell does get thicker. The annotation also updates with the new value, 0.10 inches thick. We are able to let MathCAD drive dimensions in Creo parts. If requirements changed, say maybe that a new material is chosen for cost considerations, we can easily populate the MathCAD worksheet with the new material properties and let Creo parts load the new MathCAD thickness values. Let's summarize this demo by seeing how it fits in with the Ptc Process Landscape. The process landscape shows product development and various points of views that are relevant. Product development is a set of highly cross-functional and distributed processes that span the life of the product, from planning through support. Let's focus on the engineering processes. The cell phone shell demo we just walked through shows off some of these business processes. First, system design. As much as we simplified the cell phone shell design problem, we still showed how MathCAD can be used to flow down requirements. The analysis performed in MathCAD verify our requirements. In detail design, we can take advantage of PTC's suite of multidisciplinary products to design and manage electrical and mechanical data. MathCAD can be used to analyze these electrical and mechanical components and even be extended to standardized calculations throughout the organization. Under VMV, or Verification and Validation, we briefly spoke about using MathCAD to verify requirements. What we didn't talk about was using Creo and MathCAD in conjunction with our PLM solution to not only manage data, but also trace requirements. Finally, under Variant Design and Generation, Creo provides a platform that allows you to design and manage modular products. MathCAD can also be used to analyze modular components. In our demo, we explained how we can easily change parameters in the MathCAD worksheets to drive a geometry change when there is a new or modified design. Hopefully, you now see the value of integrating the capabilities of Creo and MathCAD, and how that works into your organization's engineering processes. Whether it be designing a shell for a cell phone, air brakes on a missile, I-beam in a bridge, or a transmission shaft in a car, PTC desktop tools can help you in your day-to-day work.